Thanks. It's a pleasure to be back at the Institute. So let's let G be a compact Lie group, and lambda a class in H4 of its classifying space. So this is called a level. So I'm happy for you to think of the example where G is, say, SUN, or some connected, simply connected group, although at the end I'll consider the case of a torus. And in that case, H4 is just canonically the integers, and that's what's called the level. So one way to think of it is that this gives you a full lattice inside this vector space, and this vector space is the space of G invariant bilinear forms on the Lie algebra. And in fact, we're going to assume that this the level we take, this form is positive definite. Although that's not necessarily necessary. Okay, so this is the starting point for lots of structure in low dimensions, and I want to single out two things that one gets by transgression. So the first thing we get is, let's let LG denote the loop group. So that's the space of maps from a circle into this group. That's an infinite dimensional group just by pointwise multiplication. And one thing we get from that piece of data is a central extension of this loop group. So it's unitary. It's a central extension by the group of phases, the group of unit norm complex numbers, U1. So let me just call this LG lambda, just using the same lambda symbol everywhere. Okay, so there are nice geometric constructions for how you go from here to there. I won't say them now, but let me at least say something. We can say that on the Lie algebra level, we also get a central extension. And so if I call this the Lie algebra, which are the maps beta from the circle into the Lie algebra of G, then we get a 2 cocycle. It takes 2 group Lie algebra elements and gives me a real number. So it just takes beta 1 and beta 2, and written in terms of this bilinear form, we just integrate over the circle beta 1, apply the bilinear form to the differential of beta 2, and integrate that one form. Now, these loop groups, well, this Lie algebra, by the way, or with this extension, is an example of a Kac-Moody Lie algebra, affine Kac-Moody Lie algebra. And the representation theory of both the loop groups and these Lie algebras was studied quite a bit back in the 80s. And there's a nice class of representations which, for the loop group, are called positive energy. And were studied by Graham Siegel. And in the Lie algebra context, they're called integrable. And were studied by Victor Katz. So whenever I have a central extension, I want to look at representations of this group where the really projective representations here, but they're projective representations adapted to this particular central extension, by which I mean that a number e to the I theta here acts on the representation as multiplication by e to the I theta. And if we look at those representations, then in fact, up to isomorphism, for a fixed central extension, there's only a finite number. So these things are very discrete, and they even behave, well, very much like a compact Lie group. This is not at all a compact Lie group. It's not even locally compact, But these very special representations are very discrete. They don't deform. And so let's introduce, let's call it R lambda of LG. This is just the free abelian group generated by these irreducible representations. Let's say positive energy representations at level lambda, meaning of this particular central extension. Now, one of the nice discoveries at the end of the 80s is that this is actually a ring. So this is a free abelian group, Z to the n for some n, but it actually has a ring structure. That ring structure is named after the physicist Eric Berlinde because it came as part of a story in conformal field theory. And in fact, the multiplication comes from studying this pair of pants, where I think of these two circles as incoming. These are circles mapping into the group, so we could have two loop group elements, and out comes another one. And so in the structure of a two-dimensional conformal field theory associated to this pair of pants, that's used to give a ring structure here. Okay, so that's one kind of transgression of this data. The second transgression of this data is to the group itself, and it gives a twisted notion of G equivariant bundle on G. So here I want to think of the group G with its action on itself just by conjugation. So G acts on itself by conjugation, and we can study complex vector bundles over this group. So if we want to make an abelian group out of those, that gives us this abelian group, this equivariant K-theory of G acting on G. So elements here are represented by complex vector bundles over G, which have an action of G on it. But this, this level gives us a twisted notion of this. So we get a twisted notion of this K-theory. So to explain that, I want to give you a different picture of G acting on G by itself by conjugation. So we're going to make an equivalent picture of something I'll call that, but just think of that as the equivariant space where I have G acting on itself by conjugation. And the equivalent picture brings in the circle, and it brings in the circle by looking at a principal G bundle. So let's suppose that we have a principal G bundle. Well, the first observation is that this has an automorphism group, and the automorphism group, or the group of gauge transformations of this principal bundle, is equal to the loop group if P is the trivial bundle. So the loop group can be thought of geometrically as the automorphisms of the principal G bundle over the circle. Now, if G is connected, then every principal G bundle over the circle is trivializable, so they all look like that. But if G is not connected, then we get variations on the loop group, twisted loop groups. Okay. Well, if I fix this bundle, then let's let A be the space of connections. So this is the affine space of connections on this bundle. So that's an infinite dimensional affine space, and the group of automorphisms acts on the connections. It acts by pullback. So we can think of that equivariant space, or that groupoid or stack, however you want to think of it. I'll just write the group of gauge transformations as LG. And given a connection around the circle, there's a natural map, the holonomy. And the holonomy gives us an element of the group G. That's the monodromy around the circle, but we only know it up to conjugacy. And so after picking a base point, we get a map like that, and that's in fact an equivalence in the right sense. So in other words, a connection is determined up to isomorphism by giving its holonomy a connection around the circle. So if we want to study equivariant vector bundles here, then that's the same as to study equivariant vector bundles here. Well, here we have this infinite dimensional affine space of connections, and we have, for each element of the loop group, we have this group action. So we have to imagine that we're given a vector space at each point, and then the action there. And so we get a twisted notion by giving a central extension of this group, exactly the central extension over there. Because then what we want to say is we want vector bundles where, covering the loop group action on the base, we don't quite have the loop group acting linearly on the fibers, but only projectively, which is to say that the central extension acts linearly, and then the center, the circle, that fixes the points of the base, that acts trivially on the base, and it acts in each fiber as scalar multiplication. And so that's a kind of spreading out of a projective representation. You can think of a projective representation as the twisted vector bundle in the case when I just have the group acting on a point. Okay. So that roughly is what elements of this twisted K-theory group look like. I say roughly because, in fact, you can't do this with finite dimensional vector spaces. So you have to use better representatives. You have to use infinite dimensional vector spaces. But those won't have any topology if you do it that way. But you really use a pair, or better a Z2 graded one, where you have a Fredholm operator in between. So you have to use some infinite dimensional model with Fredholm operators to see non-zero elements of that group. Okay, so those are two different kinds of objects we get by transgressing. This one comes, so to speak, by integrating once around a circle, this class in degree 4. This one, in a sense, by integrating twice. And there's a theorem Can you see this? There's a light out. So there's a theorem of myself and Mike Hopkins and Constantin Teleman, which says that there is an isomorphism from this Verlinde ring of these representations to this twisted K-theory group. So I've shifted things a little bit. So here there's a shift in the level. This corresponds to the well-known row shift in the theory of compact Lie groups. So this is kind of adjoint shift. So this sigma is some canonical level associated with the adjoint representation. And here, well, we have the K-theory in the top degree. And so when we represent it by vector bundles or by Fredholm operators, there's a commuting action of a Clifford algebra, is concretely how you put this in. But you can think of this dually. If I take the K cohomology in top degree, that's like the K homology in degree 0. And the homology in degree 0, or in any degree of a group, has a product due to Pontryagin. You just take the push forward under multiplication. And so this has a natural product, this kind of Pontryagin product. And this one has its product, as I said, from the conformal field theory from the Verlinde ring. And, well, anyway, the theorem is that this is an isomorphism of groups. Oh, you mean here I'm adding these? Yeah, so there are different kinds of things we can do to twist K-theory, which is to say to twist the notion of a vector space. And the different kinds of twistings do form an abelian group. So one thing we can do is twist degree, which just means a vector space together with as a Clifford module. And the other one is this one that's ostensibly in degree 3. So I didn't say that this twisting of K-theory is classified by a class in H3 of G with integer coefficients. That's the equivalence class of this twisting. And again, if we take the real image, just as I did over there, we can express it in terms of in de Rham theory, as an equivariant 3-form on the group, and it's just the usual 3-form one makes from a bilinear form. It's -1/6 theta wedge theta bracket theta. If you like, it's the trace of G inverse dg cubed. It's the usual 3-form on a group. Theta there is the more Cartan form. Okay. Other questions? So that's where things were. So, this Verlinde ring, if you think about different kinds of Lie groups, even finite groups, there's a Verlinde ring for tori and so on, they had kind of different descriptions. And so what we did here is to put them all under the same umbrella and recognize them as part of topological K-theory, something well known, but a little bit twisted. On the other hand, the left-hand side is just a shadow. This ring is a shadow. It's the Grothendieck ring of a category. And so there's a category, representations at some level, maybe shifted level, LG. This is a category. So we can make a category whose objects are these representations. And one key feature is that it's a semi-simple category. So I said here that these representations are discrete. They don't come in continuous families. And the corresponding statement here is that this category is rather small. There is only a finite number of inequivalent irreducible objects and finite dimensional spaces of maps between them. But it has a lot more structure. So corresponding to the ring structure here is that this is a tensor category. And in fact, this is a commutative ring. I didn't say that, but this is a commutative ring. And corresponding here, we have a kind of commutativity, which is called braided. So this is a braided tensor category. And in fact, it has a non-degeneracy property. It usually goes by the name of modular. So it's called a modular tensor category. So this category appears in a lot of different guises and in a lot of different contexts. So you may have run into it, perhaps not recognizing it from my description starting from loop groups. So in the context of conformal field theory, it arose actually in work of Nati Seiberg and Greg Moore, who described various properties related to it. Then Reshtikin and Torayev used it as a starting point to construct invariants in low-dimensional topology, invariants of knots and links, including the Jones invariants, and then invariants of 3 manifolds. Ed Witten wrote those in terms of what's called Chern-Simons theory. And indeed, you can think that this theorem about these rings has to do with 2-dimensional theory that's topological. That's what gives a ring. And what we're after here is something in 3 dimensions, which would attach a category to a circle. No, I understand, but I mean, yeah, okay, so it would have auto-equivalences given by H3 and so on. But I think just to give a data to specify at least an isomorphism class of the category, that will give that, which at the moment I think I'll content myself with that. Right, so these modular tensor categories also appear as part of just a purely algebraic study of what are called fusion categories. They appear in the subfactor theory of von Neumann algebras, which is where Jones came up with his polynomials in the first place. It also appears quite recently now in classifying certain phases of matter in certain part of the condensed matter community, and somewhat in relation to quantum computing. There's also a construction of these where for groups that are connected, say, and simply connected, we replace the loop group by something purely algebraic, a quantum group. And so that's the kind of data that Reshtikin and Turayev used to construct it. So a long-standing question is there a category we can write on the other side and make an equivalence between this category gotten from the representations? Can we get some category from the K-theory side, just from notions of topology? And there would be an obvious guess. You could make a category of twisted equivariant sheaves, something like that, over the group, but that category is definitely not semi-simple. And so the challenge is to get something semi-simple. All right, so what I want to tell you about today, then, is work in progress with Constantin, which says that there is an equivalence of categories. I guess we could use the same letter between this representation category, this semi-simple representation category. And then we want a category that we'll call MF, which stands for matrix factorization. It still has the same kinds of decorations. It still has to do with equivariant objects on G, equivariant for conjugation. But the new ingredient is another piece of information that's transgressed from this same class, and that's called the superpotential, which defines the matrix factorization. So that's what I want to do today, is explain a little bit about this matrix factorization and say how it gives something semi-simple. So this is category of matrix factorization. And this W lambda is called the superpotential, or sometimes curving. So these come up also in physics in the context of what's called the B model. And there's lots of work by Orlov, Kapustin and Lee, Kontsevich, many people, about this matrix factorization category. So let me make two comments about this. So one is that in this category, the new ingredient is that we have a new kind of twisting of these vector bundles over G. So one kind of twisting, I told you before, has to do with projectivity, with having a central extension here. And now we have a second kind of twisting, and we have to make them work together. So usually this matrix factorization is studied without this lambda. Okay. Second thing to say is that this comes from the action of the group of rotations acting on the circle. So it's not to be confused with that central circle, but a geometric group of rotations on the circle. And when I'm transgressing by integrating over the circle, then rotation of the circle is going to be a symmetry of the integral. So that's a symmetry that we knew about, but we somehow hadn't quite used in this way. And so that's really the new ingredient here. But unfortunately, that rotation of the circle, when you think about it acting on the boundary of this pair of pants, it doesn't extend to act in the interior. And that means that what we construct, while we can construct a category, and even a piece of the structure here, which I didn't write down. It's called a ribbon element, which has to do with this rotation of the circle. That's something we can see, but we can't see this multiplication. So we don't construct the tensor category, we just construct the category, sadly. So we need a new idea to get the tensor category. Okay, so let me, if there are no questions, let me say what matrix factorization is. So this is something that actually was introduced by David Eisenbud in a purely algebraic context, algebro-geometric context, but I'll tell it to you in a way adapted to what we need. So, definition, let's let A be a complex Z2 graded algebra, or superalgebra. But you can just think that that's a ring and forget the Z2 grading. And let's let W, that's the same W as there, be an even central element. So that's the thing we're going to factor is this W. And a matrix factorization is a pair, say ED, pair of a Z2 graded, everything Z2 graded, projective module E. So Z2 graded means it's got an even piece and an odd piece, and an odd endomorphism D, whose square is multiplication by W. So this is an endomorphism, maybe I should say. It's an endomorphism of E, but over the algebra A, commutes with A. So it squares to this central element, W. So D being odd means that it exchanges the odd and even pieces. So there's a D prime and a D double prime. And factorization means that if I take D prime followed by D double prime, that's multiplication by W. And D double prime followed by D prime is similarly multiplication by W on the two pieces. So it's taking a scalar W and factoring it as the product of matrices. That's the matrix factorization. Okay. So the first kind of example is to take X to be a space, maybe a nice space, and think of the algebra as being just the algebra of continuous complex valued functions. And so then what we get, so W is just a function then, is just a function, and this E defines a vector bundle over X. This is a vector bundle, and we have this endomorphism D acting on the vector bundle. And then D squared is acting as a scalar in each fiber. It's acting as multiplication by this function on the base. So let me say quickly how you make a category out of these. So you can make a category where the objects, and this I think is Orlov. So the objects are these pairs, ED, consisting of these vector bundles. and this odd endomorphism. And morphism, say from E D to E prime D prime, is just a map F, where F is a map from E to E prime, which is even, and it has to commute with D. Like that. So it's just a map of Z2 graded complexes, if you like. But we only take the homotopy category, means we only take morphisms up to homotopy. So the notion of homotopy is that H is an odd map now. And if I take the commutator of H in the right way, H D plus DH, I think, then this should be the difference between these. So it's just the usual, it's a Z2 graded version of the usual notion. So we want homotopy classes of these. And a simple exercise, observation, is that if D is invertible, then this pair is equivalent to 0. So what this is measuring is where this is not invertible. Okay. So that's the matrix factorization category, except that to get the category, you actually take these objects and you allow this function w to change by a constant. So you have to sum up over all the different constants. In fact, in our story, we don't need to sum up over all complex constants. We just need integers, which is to say that the exponential e to the iw, or 2 pi iw, is what's relevant. Yes, I suppose that's right. Yes. Okay, so let me give you then the crucial idea of how this introduces semi-simplicity. And so the analogy is just the following. If X is a smooth manifold, maybe think it's compact, then we have different models for its real cohomology. So we have the differential forms on X with the standard Cartan differential. This is a kind of big model, meaning that this is usually infinite dimensional. So that's like non-semi-simple. On the other hand, if we have W, a Morse function, then we get a much smaller chain complex, cochain complex, this Morse cochain complex. It has a differential. And that computes, it models the same real cohomology. So this is a small model. And so putting in a Morse function makes it semi-simple, it makes it much smaller. And so let's see how that works in this context with these matrix factorizations. And so we'll just take the simplest Morse function, which is the local model, which is to say, let's let X be a finite dimensional, say n-dimensional real inner product space. And we'll let W just be the function W of the vector xi is minus the norm squared of xi. So that's the very simplest kind of Morse function. And then the theorem is that the matrix factorization category, in this case, for X, with this superpotential, this quadratic W, and we actually have to shift degrees, that this category is actually just the free category on one generator U, where U is a kind of tome class. But roughly, it's just one copy of the vector spaces. It would be as if we had a cochain complex here with just one dimension R. So the single critical point is just contributing one copy of vect, which is the kind of categorification of a one-dimensional vector space here. And so how can you think about this? Well, one way to think about this problem I like to think about is to Fourier transform. If we Fourier transform, think of this as the Fourier transform variable, then the Fourier transform of this second degree polynomial is second order differential operator, which is the Laplace operator. And then asking to solve this equation, d squared equals Laplace operator, is exactly the problem that Dirac considered all those years ago. And the end solution is the Dirac operator. And so if we do it here in the Fourier transform way, we get the Atiyah-Bott-Shapiro model of the Thom class in K-theory. So basically, what you get is to take E to be a module over the Clifford algebra with n generators, a module, that's Z2 graded, and then the operator D at any vector xi, D at xi, is Clifford multiplication by xi. That's roughly what we get. And we can just take many copies of that, and that amounts to tensoring by a vector space with no action. So that's the way in which these matrix factorizations cut us down. Well, that's where I snuck in the degree. You're right, if I didn't stick in the degree. So there's a commuting action, like the Thom class should be in top degree. So we should think of this as having another Clifford action that commutes. So in fact, the generator would be to take E to be the Clifford action, the Clifford algebra itself. Thought of on one side, the commuting side is a module, the other side is where this left multiplication goes. And that's the generator in degree n, and then it's unique. Otherwise, of course, you're right. So that's the same degree shift that occurs in those theorems with the dimension. Okay. So in our situation, we don't really have a space, but we have the space with a group action, or a groupoid, if you like. And we have to consider then what the superpotential is on this groupoid. So I'm starting to run short on time. So let me just explain it quickly. So let's think first of the case when my space with a group action just has one point, but a group acting. Think of just a finite group. In that case, the algebra would be just the group algebra. So I have a finite group H acting. And so a module over this is just a representation of H. And then the superpotential is just a central element of this algebra. So it's just a central element inside that group algebra. For example, an element in the center of H. But we could multiply it by any constant. So if we have more generally a space with a group action, lots of arrows, we might have self-arrows, then the kind of superpotential we're going to get is a function. So if this is a space X with the action of a group G, then what we get is a map from X into this group. So at every point, we have to give an element of this group that's acting, but it has the property that it stabilizes that point. So it just stabilizes the point. And since it stabilizes the point, well, we know from here it has to be a central element of the stabilizer. And in fact, it has to commute with other arrows as well. So a way to say it is that if we think of this groupoid, this is a kind of category, then what this phi is an automorphism of the identity functor on that space. So an automorphism of the identity functor, let me just connect that with the circle action, is really what's called a BZ action, where BZ here means a rigid model. It means point mod Z. So it means you have a single point with Z's worth of automorphisms. And the generator here, when it acts on something like this, is exactly acting as an automorphism of the identity functor. So you can think of this as a kind of BZ action. And, okay. Well, a BZ action thought of quite geometrically, because we have the usual exponential sequence. That's the usual circle. And if we continue this one more, then we get BZ. So what is an action of BZ? It's a circle action together with a trivialization of the induced action of the reals. That's a way to think of it. And how in our problem does the circle action come? Well, if we go back to the description, which has been erased by connections, then on the space of connections on the circle, we have a circle action. We can rotate the circle, and we can just pull back the connection. And how do we trivialize it if we lift to R? Well, given a rotation just tells you an angle theta. The lift is telling us how we got there. It's a path in the rotation group that gets us to rotation by theta. And if we have that path, then we can do parallel transport along that path. And that exactly undoes the rotation. And so if you look at what this is, well, that's just the trivialization at 1. Trivialization at 1, so to speak, is going once around the circle, and that takes the holonomy, which is what we saw before. Well, the thing that's going to mix these two actions together is that was our groupoid G mod G, but we have that lambda, which is this central extension. And so we have to lift that circle action to that stack or groupoid that's covering it. And so you have to also couple that with doing something with that gerb, which is that twisting, some kind of parallel transport in that gerb. So we need some differential version of the gerb, and then you could compute that. So that's, in words, how one can think about the formulas that maybe I'm going to write. So I think I still have good on time. So I want to tell you two things to make this a little more concrete. One is to tell you the basic map that goes into those theorems, which seem to have been erased, which is given a representation, how do we see some representative of this twisted vector bundle? And that's a construction of a kind of, we call Dirac family, of a family of Dirac operators. And then I'll show you how the theorem works in the case of a torus. So this is a construction in the papers with Mike and Constantin. And there's a version of it in finite dimensions, rather than for the loop group, just for the compact Lie group. So let me tell it to you there. So G is a compact Lie group, as before. And now we're going to fix this inner product. We had that as part of our story, but we don't have to think about starting in the loop group story. Anyway, we have this invariant inner product. And I want to describe this map, which in this case just takes a representation of the group G. And it gives us, well, it's going to be an equivariant vector bundle over the dual of the Lie algebra in this case, where G acts as the usual coadjoint action. So you can think of this as what's happening in the group. If I kind of zoom in near the identity, that's what we'll see. But it's more natural to look at it in the dual of the Lie algebra. And this thing will have compact support. And it'll be in the top degree if we do everything right. And there might be a little twisting. Anyway, what is the construction? So let's let B be an irreducible representation. So it's an irreducible complex representation of the group G. And what are we going to construct? I want to construct something which is this pair E comma D. And so it's going to represent an element here. So if this is my dual of the Lie algebra, what I'm going to give is a vector bundle over this, but it's just going to be a constant vector bundle, meaning it's just a vector space across this space. And so we'll let that vector space is going to be the representation V itself, but tensored with a copy of some spinors. So S are some spinors. spin representation. And then I have to give you a family of operators D, depending on a point mu in the dual of the Lie algebra. And that's going to be some fixed operator plus just Clifford multiplication by mu. That acts on the spinners, tensor the identity on V. So it's taking the representation, which you can think of as living over this point, the origin, and it's spreading it out to the vector space by taking the Clifford multiplication on the spinner's tensor V. If we do that, that's what the usual kind of tall isomorphism would give you. And this Clifford multiplication is invertible everywhere except at the origin, and so we would find something supported at the origin. So D0 is a fixed operator. That's a Dirac operator, I'll explain, on the group G. And it has the following effect, following beautiful effect, I think, which is that, well, first of all, D squared is some W, which I haven't told you what it is. Okay, I'll tell you perhaps in a second. And this D is invertible, except on some coadjoint orbit, O, which is exactly the kind of row-shifted coadjoint orbit that's associated to this representation by, say, Kirlov's picture. So in Kirlov's picture, irreducible representations are associated with coadjoint orbits. The coadjoint orbit goes through the highest weight, if we pick a maximal torus, through the highest weight of this representation, but it's shifted by rho. So in that case, this coadjoint orbit is always non-singular, meaning that the stabilizer of any point is a maximal torus. And not only that, we can say what the kernel of this operator D is. It's now a vector bundle over this orbit. And what it's equal to is some line bundle, tensor spinners, let's just write spinners, on the normal bundle to O. So up to kind of spinners on the normal bundle, it's some line bundle. And what line bundle is it? It's exactly the one given by the Borel-Vey picture of this representation. It's exactly the line bundle, which whose holomorphic sections, if you like, gives us back the representation. So this construction gives us, in fact, a kind of inverse to the Kirillov-Borel-Vey picture of these representations. It starts with a representation and exactly constructs this orbit together with the line bundle. And this family is a matrix factorization of whatever its square is, and its square has, well, it has the right form of this kind of finite dimensional version. So let me explain what this operator D naught is, because that leads to a kind of differential geometric puzzle that I've never been able to solve, so I can't resist telling it to you. So if I think about this Lie group, G, then this invariant inner product gives us a bi-invariant metric on G. So we have G with its bi-invariant metric. And now the spinner fields on G, well, those are the functions on G tensor this S. And the functions on G break up as a sum over the irreducible representations of V dual tensor V, and then we have S. So we can decompose under the action of G cross G by left and right multiplication the spinner fields on G like this. And the Dirac operator, since that's bi-invariant, commutes with that. And what we're doing there is just picking out one piece. And that's what D naught is. Except I haven't told you which connection to use to make the Dirac operator. So usually in Riemannian geometry, we use the Levi-Civita connection. So if we think of G, this Riemannian manifold with that metric, then there's an infinite dimensional affine space of orthogonal connections. this bi-invariant metric. And the Levi-Civita theorem says this affine space has a distinguished point, which is the Levi-Civita connection. That's the one characterized by having zero torsion among all these connections. But in fact, there are two other points that are distinguished here on a Lie group, and they lie on an affine line. Namely, the one where I get a global parallelism, so a flat connection, by using left translation, and then one where I get a global parallelism by using right translation. So there's a kind of theta left and a theta right. And you can work out that the Levi-Civita connection for any bi-invariant metric is the midpoint between those. So these lie on an affine line. Well, this particular operator that makes all of this work, you get the right coadjoint orbit and so on, is something that lies here, 1/3 the way from one side to the other. And that's a connection which appears in lots of different differential geometric and other contexts. I think it was first studied by Slabarsky, if I remember correctly. It goes by the name of Constant's cubic Dirac operator, because when you write this out, there's a cubic term. But there's a cubic term for any of these connections, so it's not a particularly... it's the coefficient that matters. It's the coefficient that makes d squared come out right. And it appears in works of Alexeyev and Meinreken in a more algebraic context, etc., etc. It has nice analytic properties. Goethe studied 8 invariants of those connections. So it has all these beautiful properties, but the conundrum is I have no idea what geometric property characterizes that point 1/3. So I would love to know. I think it's a nice, beautiful elementary question about differential geometry of Lie groups. I don't know the answer. I've been wondering for many years now. All right. Well, how much time do I have to tell you about the loops on a torus? If none, then I could stop here. A few minutes? Okay, so let me go to this infinite dimensional case and at least try to tie it together and show you how this matrix factorization shows up if we look at loops on a torus. So we'll let T be a torus, by which I mean a compact abelian Lie group, connected Lie group. And there are two lattices associated. Pi, which is the fundamental group, or better said, the closed one-parameter subgroups, and its dual lattice lambda, which are the characters, the unitary characters of the torus. And the loop group breaks up very nicely into a product of a copy of the torus itself, which are just the constant loops, across this guy, which are the closed one-parameter subgroups. And they, of course, exhaust all the homotopy classes. So these already account for all the non-trivial homotopy classes. And then there's a big vector space V. That vector space V is really, well, the exponential, if you like, of a vector space V of maps. So these are loops which in particular have a logarithm, and their zeroth Fourier coefficient is 0. So they kind of average out to 0. Okay. And when we make a central extension, it turns out that we get a central extension of this group times a central extension of that group. And this group, its central extension, is a Heisenberg group. So all the positive energy and all that comes into this part of the group, this infinite dimensional part. And its representation theory is given by the Stone-von Neumann theorem that tells you there's a unique representation of the Heisenberg group of the canonical commutation relations, which has positive energy. So here that takes care of that. And the representation theory is then very easy to work out from this finite dimensional group, albeit not compact. So what is this piece of data lambda? Well, lambda is in H4 of B of the torus with integer coefficients, and that's isomorphic in a natural way to sim2 of lambda. And sim2 of lambda is the space of even bilinear forms from pi cross pi into Z. So they're just even forms on the lattice. And we're looking at ones that are non-degenerate after I tensor over the reals. So that means that transposing, we get a map from pi to the dual of pi, which is this lambda. Let's call it kappa. And this is then an injective map. So the quotient, the discriminant group, is a finite abelian group. And so that's the data. That's the first piece of data, at least this cohomology class gives. We'll give a more geometric description. So actually, if we tensor this, there's a little bit more we can do. We can tensor with the circle group this map, and then we get a map from the, if we tensor this group with the circle, we just get the torus. And if we tensor that one, we get a dual torus. And this becomes a finite covering, an isogeny. And inside here, we have a finite group F, which is the kernel. And this finite group and this co-kernel here are both in duality and isomorphic. So in other words, this is a Pontryagin self-dual. Part of this data makes this a Pontryagin self-dual abelian group. So this class could be represented as follows. It's actually given by a principal circle bundle over T cross T, where for each T here, if I look at it here, we get a central extension of the torus. So this is a family of central extension groups of the torus, this finite dimensional torus, parameterized by the torus. Now each one is splittable. There are certainly splittings, but as a family, it's not split. And that's a geometric way to represent a class like that. So the key thing is to define the following. C, it's a correspondence between, on the one hand, the torus, and on the other hand, this finite group, say lambda over kappa pi. So this C is, well, it's the Lie algebra direct sum of the characters divided by the diagonal action of pi. So let me just say in words what it is. If I look in this direction, it's a principal bundle with fiber lambda. And the fiber over a point T in here are all the splittings here. In other words, they're all the characters, the projective characters of this particular central extension. So before I have the twisting, I would have replaced this by just T cross the characters. But now I have T cross these twisted characters. Well, why am I interested in that? So just 2 minutes. So if I want to know what vector bundles are over T, equivariant for T, that would be the same. Well, if T acts trivially on itself, T is abelian, and so I can take a vector bundle and at each point just decompose according to characters. And so if I look at the multiplicity bundle, those multiplicity bundles are vector bundles on T cross the characters, but they have compact support. Only a finite number of characters occur. So what are these twisted bundles? Well, those are exactly the vector bundles on this correspondence C. Because we now get twisted characters. That's what the twisting does, is it gives you this family of central extension, and we get those twisted characters when we decompose. Again, with some sort of compactness condition. But what does this C look like? Well, if I look in this direction, I project off onto this factor, then I get a principal bundle with structure group, this vector space. In other words, I get a bundle of affine spaces. This is just a finite set of points, so I just get a finite union of affine spaces. So this C just looks like that, where 0 is somewhere in here, is a copy of the Lie algebra. And in fact, this has a natural section, and so each of these affine spaces has a natural point in it. And these points make a finite group, which is isomorphic to this group and projects onto the group F I told you about before. Well, if we think about the superpotential, then we have to think about this circle action. This circle action amounts to looking at the action of this element T inside each character. This element T has to lift to its central extension. That's the lift I talked about. There is a natural lift. You can write formulas for all this. And so on each character, I need to evaluate that. And so we get a natural function, e to the iw, mapping c into the circle, just by evaluating these twisted characters. And it turns out this w has a logarithm, and that logarithm on each one of these affine sheets is exactly a quadratic function. And so if we replace this by this matrix factorization, then what we get is just a sum of x. In other words, we get something semi-simple. So in the torus case, you can really see very explicitly how this becomes semi-simple. Okay, I'll stop there. Thanks.